Hooke Law by Muhammad Syami bin Khairul Azman and Muhammad Nazri Irfan bin Muhammad Nazri. Content title: Introduction, Problem Statement, Objective, Method, Result and Discussion, and Conclusion. Definition of differential equation. A differential equation is one with an unknown function and its derivative. It describes how the function changes in response to particular condition or factor by expressing a relation between the function and its derivative. Only a single independent variable involved, and value of the function is specified with initial condition, and using a single degree of freedom to model dynamic system. For example, Hooke's law. Application of second order ODE. A law stating that the strain in a solid proportional to the applied stress within the elastic limit of the solid. Hooke's spring law applies to any elastic object of arbitrary complexity as long as single number can express the deformation and the stress. Fs equal negative x, Fs equal restraining force, K equal spring constant, and x equal spring stress or compression. Analysis of teaching. Velocity dx over dt equal v, coming from d2s over dt2 equal dv over dt equal dv over dc times dx over dt. Hence dx over dt equal v. Restoring force Fs equal negative kx, m d2s over dt2 equal negative kx. Xt equal c1 cos omega t plus c2 sin omega t. Y equal to exponent dx, a cos beta x plus b sin beta x. The problem: a spring with 3 kg mass is held stretched 0.6 meter beyond its natural length by force of 20 Newton. If the spring begins at the equilibrium position, but a push gives it an initial velocity of 1.2 meter per second, find the position of the mass after t seconds. The objective is to understand differential equations in order to apply them to problems that are related to physics, and to develop a mathematical model that is related to Hooke's law, and determine the equation for displacement and velocity as function of time.
From the question, the information that we got is the mass, which is 3 kg, the x, which is the length of the string that stretch is 0.6 meter, the force that applied to the string is 20 Newton, and the initial velocity is 1.2 meter per second. First, we find the value of k by using F equal kx. We substitute the value and we got that k is equal 100 over 3. Then, we use the equation that obeys the Newton's second law, which is m d square x over dt square equal negative kx. We transfer the kx into the left side and then it equal to 0. Then we substitute the value into the equation. Then it becomes 3d square x over dt square plus 100 over 3x equals 0, which can be written as 3x double prime plus 100 over 3x equals 0, or 3r square plus 100 over 3 equals 0. Next, we calculate the root of the equation, which we get r1 and 2 equal plus minus 100 over 3i. Since it's a complex conjugate root which has an imaginary number, we can calculate the alpha and beta value. Then we insert the value into the equation y equal e power of dx, and in bracket a cos beta x plus b sin beta x. When x equals 0, it is at an equilibrium position or not moving. So insert, then we got 0 equal a cos 0 plus b sin 0, which we get a equal 0. Then we got x t equal b sin 10 over 3x, and the initial velocity is 1.2 meter per second. Then we differentiate x t, we got vt equal 10 over 3 b cos 100 over 3x. Then we insert the value. We got b equal 0.36. Then we got two general equation, which x in unit of t equal 0.36 sine 100 over 3x, and then v in unit of t equal 1.2 cos 10 over 3x. Since the problem want the position of the mass, so the final answer is x in unit of t equal 0.36 sine 10 over 3t. Result and discussion. By Hooke's law, k equal 0.6, which is equal to 20. So k equal 100 over 3 is the spring constant, and the differential equation is 3x to the power of n plus 100 over 3x equal 0. The general solution is x in unit of t equals c1 cos 10 over 3t plus c2 sin 10 over 3t, but 0 equal x0 equal c1, and 1.2 is equal x prime 0 equal 10 over 3 c2. So the position of the mass after t second is xt equal 0.36 sine 10 over 3t. This graph shows the movement of the spring based on the equation that we get. Conclusion. This project shows that Hooke's law has provided an incredible insight into Newton's second law of motion with relation of application of ordinary differential equation. This also shows that application of second order ordinary differential equation is great tools to study about spring motion behavior. This study become a foundation for further research in order to understand Hooke's law and application of ordinary differential equation. That's all from us. Thank you.